All right. Do you guys see that's recording?
Yep.
All right, perfect. So today we're going to be discussing files, specifically how files are loaded into memory, and we're going to be mainly using the ELF file structure to do this. Ben, what is the ELF file usually used for?
Linux executable.
Yeah. So Linux, a lot of embedded systems, stuff like that. All right. So what do you think is the most, or what are the most important parts in an executable file? What does the system need to know?
Which file it is first. So I think the magic number.
Okay. So the magic number, which tells us what type of file it is. What else?
More, I don't know.
More. So architecture. Yeah, that's a good one.
Yeah. Okay. Architecture.
Yeah. So parse it, architecture. Any other guesses before I start sharing my screen?
No, not really. No.
No? All right. Let me go ahead and share my screen, and we can start going over it. Debug info, that is important, but not all files are going to have debug info parse. All right. So can you guys see the screen?
Yes.
Okay. Once I can get the chat pulled up over here. All right. Sorry about that. All right, so what's important for a file is it needs to know, different code segments, right? It needs to know where the data, so things such as strings, other constants that are too big to be in the code sections. So do you remember when we were going over assembly, we had the section where, we had the data section at the start. It's like, let me actually pull that up. So we have the skeleton file, and see we have the data section where we have constants that are too big to be in the actual code. And then we have the code section that contains our actual instructions. And then, we reference our data section, right? So those are, the main parts that we're going to need. All right. Have either of you guys really gone into the ELF file format very much, or not really? Just, you have. All right, Parth, what have you gone into for the ELF file format? Debug info? Okay. So what are the main sections? I guess you can see one is the read-only section. Okay. I'm talking about the main headers. Do you know the main tables that we have? Okay, so what are the three main tables that we have in an ELF file? Tables, headers, I'm using those interchangeably right now. Ben, do you know?
Data.
Right. So the three main sections that we're going to have is we're going to have the ELF file header, we're going to have the program header tables, and then we're going to have the section header tables. All right, so we're going to walk through them right now. So the first thing that we have is we have this ELF header, right? So this tells us a few things. It tells us what type of file it is, so that's what Ben said. We have, the magic number ELF here. It also tells us this, if it's 32-bit, 64-bit, as Parth said, right? So in this table here, I put them as one section. However, under the actual elf.h, if you look here, so this is from the Linux, from actual, Linux. It's not done like that. The ELF number is a bit bigger, and it includes this information, this identification information, right? But I segmented it out into this table so you could see it a bit better. So that has, some padding at the end. It has the ABI version. It has target operating system, some versioning information. But the most important things that we really have to focus on is we have to check for the ELF magic number, we have to check for 32-bit or 64-bit, and then we have to check for NDNS. You guys know what NDNS is?
Yep.
All right, Ben, what's NDNS?
The byte order is reversed in little endian. Yeah.
So it's basically saying, which way we should read bytes to represent data. All right. So then after we have, the identification section that just basically tells us we're using the right file, we are going to have a few other bits of information. So we have the type of file, so if it's executable, if it's a dynamic loaded, stuff like that. And then we also have the target architecture. We have this versioning number again. We have the entry point, which is going to be where we're going to start processing the actual code. Then we have the offsets to the program header and the section header tables. And then we're going to have some flags that I'll go over a bit more in a second. And then we have the size of this header, which is going to be, either, it's going to be, just the size of this. So at the end of you already know the size. So it's going to be, 3440. Then we're going to have the size of the header table, or of each entry in the header table, which is used to, we'll go over that later, I guess. The number of entries there, and then we have the size again of the section table header entries, and then the number of those. And then here, any guesses on, so Parth, you said you went into it a little bit. Do you remember what this part is used for? Without, I guess you can look there. We'll go over that too. So I made this, you looked at ARM else, it's going to be the same. So ARM is, the architecture is just set here, right? So this eMachine, but the actual header is going to be the same for all of them, any type of else, because that's just the format. All right, so I made this little bit of code here that we're going to go through. So this else.h is pulled directly from the Linux source, so you can just look through that. I just pulled it here so that you guys could also look through it. And then we have this little example file here, which just has another function. It has some strings. It has some globals, stuff like that. And then I made this parse elf.cpp. It's commented. You guys can go through it. So we're going to look at the actual elf header here, right? So what should we expect for this file when we run this command? Any guesses on what we'll see here?
No.
So let's take a look at example.elf, right? So we see that it's 64-bit, right? So what number are we going to be seeing under, in some of this code here? I guess let's just run it. All right. So those are all the tables, all that fun stuff. All right. Let's put this side by side. Did I actually remove that? I might have removed that information there. Ah, it looks like I did. Okay. So never mind. But okay. Sorry, I'm gonna have to edit that bit out. So originally I had set this so that it showed us all of this information here, all the identification information. So we could see, so if we actually look at the identification information for this one, you can see that it's going to be a 2 here because it's a 64-bit binary. We can actually do hex edit on it, and I'll show you. So if you see here, this bit's a 2. So here we have our magic number, right? And here we have our 2. Then we have the 1 showing NDNS, all that information. Does that make sense?
Yep.
Just for that, how that header is done. Okay. Awesome. Okay. So then the next thing that we want to look at is we want to look at the section header and the program header tables. So I'm actually going to go through all the information first, and then we'll look through the file because it might be confusing jumping back and forth as we just showed, or as I just made a mistake. So the program header table is basically just a bunch of different entries and each entry is going to look like this. It's going to tell us what type of information it is. It's going to tell us if it's a loadable segment, if it has dynamic linking information, just stuff like that. So if we look at this file here, we can see that we have quite a few. So these are the section headers. We see that we have quite a few of the program headers here. And then you see the type changes here, but a lot of it's, 4, 2, and 1. We see a lot of ones. So it's just a loadable segment. Then after that, what we need to know, the important things that we need to know is we need to know the offset. We need to know the virtual address, but this is a lot of times just going to be 0, which I'll show you later. But what the offset basically tells us is if we have memory blocked out after we load a file, this offset is basically going to be the virtual address because it's the offset from the start of that data. So when you load, an ELF into memory, if you were to do it manually, you'd look at the program header, right? You'd malloc space for whatever amount of space you need for the code that you want to run, and then you're going to go through all the program headers, and you're going to malloc, or you're going to basically move the memory from the file into that area, right? So let's say we have this program header, right? So we have the offset from the file where we can just grab it, and then we can just move it to where it should be in memory. It's going to be a very basic move. We don't have to worry about relocations or anything. Does that make sense, sir? Ben, that might have been confusing.
Yeah, I think I understand it.
Okay, so let's say that this section is in the 1000th byte, starts at the 1000th byte offset in the file, right? This is going to be 1000 bytes, this offset. So we know that from the file, it's at 1000 bytes, but then a lot of times in memory, it's also, we're just going to map it to 1000 bytes in memory. And then if we have to do any relocations, we're going to do those after reading the section headers. So then after this, we just get, so this, so you have your virtual address, you have your physical address, which we probably won't have to worry about in most cases. You have the size of it, and then you have the size in memory, and then you just have a bit more information. So this is, it's important, but it's not too important for the actual loading of the ELF file. The actual loading comes in with the section header table. So this is the fun one. So with a section header table, we're going to have a name, right? However, what's wrong here? Size of 4, right? That's not going to be enough for any sort of name, right? So we just have this offset, right? And the way that it works is this sh name is actually just a number. And then what we have to do is, so remember here, I said that we have this, this field, right? This index. Yep. Mm-hmm. So let's say this index is 5, right? What that means is that the 5th section header is going to be the, let's see if I wrote it here, it should be here. It's going to be that the 5th section header is a type of string section, and it's used for all the names of all the section tabs. So we'll go through the code to actually make that be more sense, but it's a pretty cool system. I enjoyed it a little bit. And then we have the type of all the section headers. So it tells us if it's program data. So program data is going to be, this code stuff, right? It tells us if it's a strings table. So strings tables could be, function names. We have a strings table for,
resolving.
For what?
Resolving, the libc resolve used at string tab.
Yeah. So we have that. The strings table is used for all the section names, as we have another one. So this is also a pretty important one. We have our symbols table, which we'll go into depth more later. But that's also one of our very important ones. We have 2 relocations ones, which are also going to be pretty important that we're going to look over. And then the rest are there, but we're not going to focus on those too much. So we're mainly going to focus on symbols table, string table, relocation tables. And then we're also going to focus on the no bits. So the no bits is data that is written to, basically, over the course of the program execution, right? So let's say that we know we need to allocate 500 bytes because our program is going to use 500 bytes of memory during runtime, right? That it needs to write and change. So basically like almost RAM. So this tells us how much we have to allocate. So we'll go over that a bit as well. So then after that, there's a few more fields. You have the virtual address, which is going to be 0 in a lot of these cases. Does it contain heap size 2? I don't know off the top of my head. Sorry. I will look into that though, and I'll let you know. Sorry, Parth. I think so though. I'm pretty sure it is heap size as well. So we're mainly going to be looking at this offsets, and then we'll go over the link and info because it's used differently for different sections. Yeah. So for the section headers, we have a few different types. We have, the text, which contains code, data, which is data, and then the BSS. So these are the main different types of section headers. Right. So now let's go over the symbols table. Well, actually, here, let me go through. So what I did here with this ELF thing is this goes through, this gets all the program header tables. So here you can see these are the different program headers that we have, right? We have the load segment, interpreter segment, dynamic, right? And then we have all the section header tables. And the way that this works is when we looked this up earlier, scrolling all the way up again, sorry. We saw here that this is 29, right? That the index that we have to look up is 29. So then if we go all the way down, we see that it's actually here. So this is going to be the 29th one if you actually count. So see that there's several different string tables. However, this is the one that's used for that information, right? So let's go through and see how we actually parse that, right? Because just talking about it's not going to be too helpful. So the first thing that we're going to do is when we read the data, we're going to just set the start of the data, right? The bytes that we read to be a pointer to the ELF header, right? And that's one of the reasons why for this low level stuff, you want to use C and C++, just because you can do nice things like this, right? I can just say, hey, it starts there. That's what it is. Then we have the header, right? We have our two offsets because this is how we get the program header and the section header. We just use the offset from the header, right? So the loader uses the header for everything in the actual file. And then, here we go through, we know that we have this many program header entries. I just increment it because I say that it's an array basically. However, what the program does is it uses the size of, because if you remember when we looked at the actual ELF header, we have the size of each one, right? Of each entry. However, the size of each entry is just going to be the size of a header, right? Does that make sense? I feel like I lost you guys there. Ben, questions?
Yeah.
All right, go for any questions.
I don't understand it at all.
Okay. What part are you lost in?
So from the where was it? The offset from where was it?
The offset. Are you talking about these offsets here?
Yeah.
Okay. Yeah. So when we look at our memory, right? Let me go back here. Okay. So that we see that our first offset is 64, right?
Yes.
All right. So if we are going to go through, oh geez, 64. What's 64 in hex again? It's not 100. It's
40.
40. Yeah. So that it's going to start here-ish. Okay. So this is going to be where it starts, basically, is what we say. That's a bad example. Let's see. I want to explain this better. Okay, I know. So we know that. Okay. Sorry, one sec. I know how I want to explain this now. All right. So we know that the section headers are going to start at 14,864, right?
Yeah.
Okay. So we're going to take that and we're going to say that that is the start of our section header entries. Like, so the start of the table with all the entries for the section headers is going to be at 14,864. Okay. I'm going to use this one as an example because it has all the strings, so you'll be able to clearly see where it starts. We know that this is the 29th entry, right? Is where all the names for the section headers are stored. Yep. Correct? Okay. Yep. So we're going to do 29, and we know that the size of each entry is going to be 64. Okay. So we're going to multiply that. So we're going to do 29 times 64. Okay. So that's 1856. Let me open up another terminal just. But 3810 is going to be our section header, right? The offset to that from the start of memory. So from the start of the file's bytes. So if we do bytes plus that number, we're going to get the header, right? The start of the section header table. Okay. So then we know that the 29th of those is going to be the start of that strings lookup. Okay. So let's see if this prints it out right. Maybe I was just doing the math wrong. Who knows? That could be. So the offset to that is going to be header, and then we're going to get from header, with the main header, we're going to get the index, which is just 29, right? So let's get that. Why did I type wrong? Oh, yeah, because it's not not hex. It's not a number, right? And then let's say we want to get the first one of those, the first string, okay? So we're getting the first string. Yeah, no, parse was right. I was being, yeah, no, parse, I know what you mean now. Yeah, so the addresses. Geez. I am tired today. Okay. So, yeah, sorry, parts about that. So the section does tell us the offset, right? So we can't just automatically assume that that's the right one. So we know that the section header, right? The 29th section header, and then we are going to get the offset from that one, right? Okay, here we go. Okay. So we have the offset now, and we see that the offset of that string is at 3907, right? Now it's gonna work. Oh, yeah. I had all this ready in my mind for Tuesday, and then I haven't looked at it since Tuesday. So yeah, we can see 39 and then 07 is the start of this. Perfect. Yeah, see here? Yep. So does that make sense how we get the address there for each of these then? So
yeah, I think I understand.
Exactly. Yeah. So not really a linked list because linked list, each of the tables would know the address of the next one, but think of it more like an array with a value. No. So this array of like all the headers basically is just an array of these, and then these tell you where you need to go, right? So the offset tells you where you need to go. So a linked list would know each of the next one. It's definitely more of an array part.
Okay.
So after having so we go through all of these, and then we can just go through, right? And then we can read the names, we can read what type it is, right? So we go through all of these, we get all the section header names like this though. So what we did is basically the same thing that we did here. So we got the offset of that one section, right? And then we get the current section's name. Like the name is going to be a number for how many it increments. Or so like if we know the second string starts at position 11, this sh name would be 11. It wouldn't be 2. So it wouldn't be 2 for the second string. It would be the offset at the start of the string. Because the way that these sections work is you can see that it's just a bunch of null terminated strings back to back, right? So it's not at some sort of offset. It doesn't space them out or anything. And the reason it does that is because that way you can just go to the start of one and then you get the entire string, or you can even start halfway through one. Some of the compilers will try to do things like that to save on space, right? So let's say at some point we need I don't know, we need hash, right? We could say, instead of, having another string that's hash, we can just say our string starts here, and then we just get hash. Does that make sense?
Yep.
Good. So we're on track. So that's how it gets all the names, right? Which is really cool. So then once we've gone through, we go through here, we get the name, and then we get the type of each one. And then type, the way that I did this is I just made, this array here, and we basically just offset, and I'm just getting these types, right? These types here. So that's how that code's done. But so we go through and we get all the types. So the first thing that we're going to look at is we're going to look at the symbols table. So you can see here, this is the symbols table, right? All right, so now let's actually discuss what the symbols table does. Are everyone good here though for how this works? How we got to this point? How we iterate through the sections, right? Does that make sense?
Yep.
Okay, perfect. So what the symbols table basically does is it's a section. It tells us the spot in memory that it is, then it also tells us what type of symbol it is, and then the visibility, right? So symbols can be local, they can be global. They can, and here's a bit more information if you actually want to read through this. So if we actually look at just the symbols here, we can see some stuff that you might recognize, right? So let's see. Here you have the name of the file, right? That's just a type file. Here you have printf, which is an external function, right? So the symbols is going to tell us, it's an external function. It's global, we can use it anywhere, right? And then we're going to use this to look up the function, right? So we have some, a lot of these are going to be virtual addresses. They're going to be relative. We'll go over how it calculates that. There's some absolute addresses, and then for the external one, it basically just tells us that we have to look it up externally to get the address for it, right? So like put s we use externally. Other like the different text ones are going to be internal, and they're going to be different functions and stuff. So like 8432 is a function, 8480 is a function, 8544 is a function, right? And if we actually if we do that, we can probably see, yeah. So you see, the section, the names that we have up there, right? So 1160 is going to be some memory, but it's going to be mapped differently, of course, right? But this is basically how you get all the symbols. All right, so you calculate them, and I have it written in here how to calculate them. So, so if we have symbols, so we have the external one where we can just look up the name, right? We have the absolute addresses where we can just say, hey, our value in this section or that item is going to be the address, and then we also have the relative addresses. And the way that the relative ones work is we have to look up. So we have this little bit of extra information here, and we basically use that. It's going to be another table as well. So we use them to look at each other. So the symbols has this is going to be a symbol, right? So you have the name, which is going to be just a string lookup that we have. However, it still uses this, right? The main name lookup one, right? Because we have to reuse some of those names. Then we have info, which is used. I'll show you how that's done. And then we have the associated section index. So this is going to be how we look up the relative values. So the info, the way that that's done is we have the high bits and the low bits. Do I talk about that here? No, I don't. So here, so you see here for symbol, we have the symbol info. So we know the type, right? And then we know the information. And it basically, as you can see, a lot of these info ones will store information in like half of it. So you get the binding for the lower bits, you get the type for the higher bits. Here you get the symbol for the lower bits, you get the type for the higher bits, stuff like that. Does that make sense? How we get the information there? Okay. And then we can just look up information using that as well. So here, for example, the binding, right? We can see that it's a global binding, weak binding, etc. Because we get the high order bits here for the info, and then we get the lower order bits here for that. And then we can just offset it there. So that's how that info component is used. So does that make sense how we get all the symbols? Yeah. Ben,
yeah, I know, I understand how it works, but I can't explain it. So I have to look up the video another time, then maybe I can explain it next time.
Okay, so is there anything else you want me to add here right now for this?
I don't know. Go on.
Okay, so but you know why we need the symbols, right?
Why we need the symbols?
Yeah, why do we need these?
Oh.
So like if put s is called, we need to know where that code is, right?
Yeah.
Because put s isn't in our local one, right? So our file by itself has no clue what to do with put s, right?
Yes.
Because that code just isn't there. So the symbols lets us load, figure out, where it is, right? We know it's an external one. We know that we have to look it up, right? And in our system, we can look up, that module, and then we can load it into memory and actually use it. Does that make sense?
Yes.
Okay. And then these virtual addresses, what they basically let us do is they let us kind of map it into memory, right? So we know that section, the section is going to be mapped here. It's going to be a type global. It basically lets us set memory a certain way as well, right? Because I talked earlier about how, like each of these has different permissions, right? So like this is the text is executable. .bss is read write. So you can basically go through and we can mem protect memory as well while looking through these symbols. Does that make sense?
Yeah.
Okay. So let's hurry up because we're running out of time. Sorry about that. String tables. I think the string tables make sense to you guys, right? They're just
string
a lot. They're just
strings.
A lot of strings. Right. We can go through. We can read all the strings. You see here. Here's our the string table with all the external stuff that we need. The putf, the printf, the libs. Here are all the strings for other parts. These are all the strings for the sections, right? So that's just string table, nice and simple. BSS is the memory that is zeroed out, and then we have to use it. So the way that works is the BSS tells. It's not going to have a bunch of zeros, right? But it's going to say there were more of these. That is, there were at least 2 of these. Yeah, this data used to have. I will have to update the code later, but that's weird. Anyways, what it basically tells us is that we have to allocate 8 bytes at X memory, right? So it's not gonna have. So a lot of this, the file has the memory there, and we just copy the memory over. It's not gonna have a bunch of empty memory, but it's gonna tell us you need to initialize empty memory at this location. So that's what this segment does. Does that make sense? having a bunch of zeros in a file is just a waste of space, right? Because they're not used for any sort of information, right? That's the same reason why we don't, copy, put s, printf, all that code, and put it into our file, right? Because there's ways to look it up. So all the data in the file is just used to look up things. Okay. Then we have this relocation section. So the relocations is fun. So a lot of times we're gonna have to relocate things, right? Especially after it's moved into memory, we have to move things around. Some of those external calls we have to move around. Different sections we have to move around because they might have been copied into memory one way, but then when we actually have to access them. So like, let's say we move one function into memory at location X, right? But then the relative. Do you guys know how calls work in assembly?
No.
Parse, do you know how calls work in assembly? No, not a jump, a call. Okay, this will be fun. All right. So you remember our handy opcode table?
Oh, yes.
Okay. Let me pull that up. Here we go. I think it is 8E, maybe. No. E8. Okay. So can you guys see this?
Yep.
Okay. So the way that calls work is, let's say I'm at memory position 0x40, right? And I have a call. And the call instruction we have is E8, and then we have 32-bit or 16 or 32-bit number, right? Basically telling us an address, right? So we have the call and then we have a number. So it's gonna be something like call 18, right? After it's like read out, right? I'm not gonna make up some opcodes right now. So we have call 18, or we have something like call -20. So the way that works is that the code will jump to a location, to a memory address based on this relative location. So if we're at memory 40 after we've read the call, so like the end of the call is at 40 and we have 18, we're gonna jump up to like 58, right? If we get the second call, we jump to 20 as our location of where we are in the file, right? Because all calls are gonna be relative. And then, so the reason that we're gonna have to relocate things is, let's say we map two things into memory, and then the second one thinks that the first one is 100 bytes away from it, but it's actually mapped into memory, like 1,000 bytes away. So we have to map them so that all the relative calls are gonna work. Does that make sense?
Yep.
And later, when I go into game hacking, we'll see this a lot more because we're gonna have to basically hijack those relative calls. And it's a technique called hooking, and you basically hijack the relative calls and then use them to point to your memory instead. So let's say that we have a call to a certain function in a certain spot. Let's say we have a call to take damage, right? And then instead of changing that function to do whatever we need, what we can do is we can take the bytes, like the 5 bytes that do the call, right? Because it's going to be E8. Yeah, it's E8, right? Where'd the call go? You see call? Yeah, E8. E8, and then 4 bytes for the actual number, because we're going to be doing 32-bit and 64-bit game hacking. But then in the actual file, we can rewrite these to go to memory that we want to go to, and then we can make our own function for the take damage. And then we can say, instead of taking damage, we want to gain health every time we're shot. And I mean, for an example like that, it's not really worth it because you can just go in and change the bytes for that actual thing. But what it's really nice for is if you want to add a lot more logic, right? Because you only, with everything's relative offset, so you can't just add bytes in randomly. Otherwise, you have to change every single address in the entire file. And that's going to get caught pretty easily by ANSI, right? But if you only have to change 4 bytes, and then you can make it look at your own memory, and then you can make a function however long you want, right? And then you also don't have to work, changing stuff in assembly. You can, write a C or C++ function and have it call that. So we'll use that a lot in game hacking. But anyway, so there's these relative calls, right? So we're gonna have to, obviously relocate them, right? So we look through. Oops, I spelled that wrong. And as you can see, we have a few relocations here. So it's mostly to like dynamic stuff. So all the dynamic calls, right? Because when we looked earlier in symbols, we know we have these external calls, right? The put s. So as you can see, a lot of this stuff is these headers are for the dynamic stuff, right? And then if you looked under the strings up here, I guess we're just going to do the string command again. The dynamic stuff was this, put s, the print s, stuff like that, right? So when we relocate, we're gonna have to move this into memory because we know where those symbols are, right? But they're not in our file. So, and in our code, we're gonna have relative offsets to those symbols, right? So they have to be mapped into our file so we can actually use them. So that's what the relocations do. And then you have different types of relocations. So you see here how some have all the ones of type 8 have this addend, right?
Yep.
So that basically just gives us a bit more math. This table is very, very tiny. So we have the rel and then the rel 8, and here this table is really bad. But as you can see, you have all these different types with values here, and then you do different calculations based on them. Yes, thank you, Con. Is that a much better quality? Okay, so for 8, right, we have b plus a, right? So that's going to be we take the base address at which the shared address is loaded, and then we relocate it to the addend, right? Then we also had 6, which is 6 and 7 are just the s, so we just the value, stuff like that. So that's how the relocations are done. Does that make sense?
Yeah, I think yes.
Okay, Parse, does that make sense to you? Ben, questions, go. Some calculations, yeah. So I'm not going to go into how all the actual calculations are done because you can just look up this table, right? Okay, but Ben, what was your question?
How does relocation work? But I have to read it on my own, and I understand it.
Okay. The main thing is why we do relocations. Do you understand why we need to do relocations at times?
So when we load a external function like printf, we need to tell where it is actually. Yeah.
So if you're loading printf, what are you going to do with it normally, right? You're gonna put it into memory somewhere, right?
Yeah.
Okay. But then our actual code, after we've mapped all our code thinks that printf is at a certain location, right? And if we try to access that location and printf isn't there, there's going to be issues, right? Mm-hmm. So we have to relocate that printf code and put it into that location where our relative offsets think it is.
Okay.
Does that make sense?
Yes.
Yeah, you can need to relocate for internal functions. you do it sometimes, but mainly it's for external stuff. You can do some funky stuff with loading though, right? Technically, you could really mess up somebody's decompiler, not like mess up break, but like make it useless by kind of messing with that stuff, because you can change all the bytes in a file by hand. So you could make it relocate certain stuff, like internal functions, parts if you know what you're doing. But in most cases, it's going to be the external stuff. Yeah. Ben, you have another question?
Nope, not at all.
No, not at all. All right. So that was kind of a very quick and dirty. Sorry about I'd forgotten, not like forgotten, but just I blanked on a few things here. Just because I haven't looked at it in a while. Any other questions about anything that we discussed today?